Okay, in the previous video, I missed out this last part of the question in this example, which is finding the energy stored in the spring when it's extended for 0.08 meter. So what you need to do is you just use the equation of E equals to kx squared, or half fx also can. Okay, then you sub in the value of the k and also the x, then you should be able to find 0.2 joule. All right, so let's move on. Combined spring constant. So we have actually done this in the previous practical, where you have different arrangement of spring. Then you try to find the k, the extension, and all that. Okay, so now you can refer back to that to revise on what you have done. Okay, so let's say we have a spring having a spring constant of k. Then if you arrange that in a parallel connection, so it will become 2k. Okay, so parallel become 2k, and the spring system actually becomes stronger or stiffer. Then if you arrange it in series, it actually becomes less stiff. Okay, so means that the value of the k actually indicate how strong is your spring or how stiff is your spring. Okay, so now you know why the hammock spring or the baby sarong spring, they are made of so many parallel springs. Okay, so they're strong enough to hold the baby, right? So now I have just a revision for you to find the combined spring constant. Okay, so you do for A and B and submit as an assignment. So if you forgot how to do that, then you can refer back to the previous practical that you have done. All right, so elastic behavior. A material exhibit elastic behavior if the deformation produced it disappear after you remove the force. Okay, and then not only that, it return to its original shape and size. Okay, so this deformation totally disappear means that it will go back to its size. Right, so it's like the example is the spring itself. So you let go, then it go back to its original spring. So sometimes it's not the case. If you apply a force that is a bit too large for it to withstand, then it will actually go permanently deform. It cannot return back to its shape. So sometimes when you last time when you do the practical, right, the spring, some of them are it's like loosened already, it got spaced out a bit. So that's because you extend it for too long time, or you put a force that is too large on it. Okay, so that's why I remember I told you that some of the spring is not in very good condition. Okay, so that's because they are not elastic anymore, so they have actually not obeying the Hooke's law anymore. So after the point P here, if you continue to add force to that, and they don't, if you remove the force somewhere here, and then they don't go back to the original point anymore. So I will further elaborate on this later. Okay, so elastic behavior. Yeah? So now I have a exercise here for your submission, okay, as a homework. So I don't go through this. Yeah, so you try to do this. Actually it's the same thing. Now let's move on to quantities that you haven't seen before. It's called the stress. The other one is called the strain. Okay, it's related to force and also the extension. Okay, stress is defined as force per unit area. Okay, force per unit cross-sectional area. Symbol is actually this sigma here. Okay, is Newton per meter square, is like Pascal. So it has the same unit as pressure, but the idea or the concept is different. F is the force, A is the cross-sectional area. So in pressure we don't say cross-sectional area. In pressure we say the area normal to the force only. Okay, it's not cross-section. But for material like this, let's say there's a wire of or a piece of metal, then its cross-section area is what we're looking for. Then the other one is strain. Okay, so the equation is epsilon equals to x over original length. X is the extension. Okay, L naught is the original length. So it can be extension, it can be deformation. Depends on whether you are trying to pull it or you're trying to compress it. okay, but both case you can use x over original length. Okay, that's strain. So let's look at one example here. We have 100 Newton force act on an area of 20 millimeters square. Calculate the stress. So you can straight away use sigma equals to 100 divided by 20, convert into meter. That will be 10 to the power negative 3, and then you square that. Okay, next question. We have a bar of length 2.2 meter stretch to a distance of 5 mm. Calculate the strain. So it's the distance, which is the extension, 5 times 10 to the power negative 3 divided by 2.2. Okay, so simple idea. Then I have this case here. This one as your homework, okay, for submission. All right, then we go to the next one. So tensile stress and strain, this is just another summary of stress and strain. So one of the type is the tensile. So you have tensile, then it will stretch the thing. If it's compressive, then it will become smaller or shorter. Okay, either way, I mean either of these two category, you can make use of the same equation shown to you just now. Okay, so now we have these two different graphs. One is force times extension, and one is stress over strain. Okay, if you plot this for the same material that you're trying to do an experiment to that, as in you put force and then see how much it extends, and then you plot the graph. So on another table, you calculate the value of the stress and the strain, and then you plot the graph. It will look exactly the same. Okay, so we say force is directly proportional to extension, and stress is directly proportional to the strain. So then you might be thinking, why is it so troublesome that we had to have another set of stress and strain? But because stress is like force and strain is like extension. So here's the reason. Okay, we have the K is the force over extension, and then the gradient of the stress strain graph is actually called the Young's modulus. Okay, it has a different name. It's not called spring constant anymore. It's called the Young's modulus. So let's say we are trying to compare K for two different wire, and to do that we have some limitation, because no matter how precise you cut the two wires, definitely there will be some slight difference in the length of the two wires, and the thickness you cannot also make sure that they are 100% equal, because it might have some uncertainty or inaccuracy when it is manufactured. So to make a fair comparison, okay, we use force per unit cross-section area and extension per unit length. Okay, so no matter what is your how is your area, cross-section area, different from both case, we just divide by their corresponding cross-section area and their corresponding length. Okay, slightly different doesn't matter, because we are comparing the per unit cross-section area and the per unit length. So in that sense, it becomes the property of the material. Then you can have Young modulus for different types of metal. So when you talk about spring constant, and then you compare it with different types of metal or material, that's not a very good it's not a very good what do you call that, the properties that you're trying to differentiate. So Young modulus become a better description. Okay, it's not affected by the length of the area. So Young modulus, it is an elastic property of material. But when this is not the definition. Definition actually is the one that I showed you just now. Definition, you can just highlight this. Definition of E is actually stress over strain. Okay, generally it's called the elastic property. So here I'm going to show you some examples. it will be usually around 10 to the power of 10 to 10 to the power of 11. Some is 10 to the power of 9. Okay, so no need to memorize, just remember about the order of it. Okay, so now we have one example here. This Brennan bridge cable has a cross-section area of 0.055 meters square, length is 110, made of high tensile steel of this 2.6 10 to the power of 11. So this is the E itself. This is the L or L naught. This is the A. Okay, calculate tension is this. So this is the F itself, kilonewton. Yeah, calculate the stress applied on the cable. So stress is force per unit area. So you sub in 950 K 0.055 meter squared. Then you should find the answer. Okay, extension of the cable. This one you don't have a direct way to calculate that. You have to pull in the equation for stress and divide by strain. Then you put in the 2.6 10 to the power of 11, the stress you have found there, and then you have the extension over original length. Original length is 110. So from here you can find the x actually. All right. Okay, so this one I will describe or elaborate in the next video. I'll see you then.